Hello APC Mechanics students in Unit 3 Work Energy and Power 3.1 Forces and Potential Energy Part 5. Section 1 Gravitational Potential Energy near the surface of a planet. An object of mass m is placed in a uniform gravitational field G near the surface of a planet. Then our system consisting of mass planet possesses a gravitational potential energy UG. Now why it is healthy to talk or to discuss gravitational potential energy, because in the previous class we mentioned that the gravitational force is a conservative force, which means that analytically it would be associated with potential energy, and it is known as the gravitational potential energy UG. To be convinced that the system indeed possesses energy, because if the object is left from a certain height it will fall freely, and the gravitational potential energy would be converted to kinetic energy under the action of the force of gravity, which is a conservative force. So remember that also we have cited the fact that gravity is a conservative conservative forces convert energy from one form to another. So whenever the object is at a height h from a certain level, it will fall down, and the associated potential energy, gravitational potential energy, will be converted to kinetic energy under the action of the conservative gravitational force. The aim of this section is to determine the expression of UG near the surface of a planet. Near the surface of a planet, the pull of gravity is given by minus mg. The vertical position of the center of mass of the object is given by y. Now here, why we have a minus sign? Because the positive direction is chosen to be up, so gravity is pointing downward. For this reason we have a minus sign. Now y would be the vertical position of the object, and if you want to be more precise, the center of mass of the object. The gravitational potential energy UG can be determined using this relation. Delta U is minus WF. So here we're trying to find the expression of UG that represents the gravitational potential energy, which is minus the integral of yi to be yf of f dot dy. Here we're assuming that the initial position of the ball is the ground, and we have lifted the ball into a final position given by yf, where yi is the initial vertical position and yf is the final vertical position. Replacing in the above integral we get, so we have replaced the force F to be given by minus mg. Now minus and minus, they would cancel, and we're left with the following integral. Now mg is a constant, it can be dragged out. Now here we're integrating for dy, this is 1, so that would be linear of yf minus yi. And we can say that the difference between the final vertical position and the initial vertical position is given by h. Now the change in the potential energy is given by mgh. Now here we need to do the following. We will define the PE level at the initial vertical position yi such that the potential energy ui at the PE level is 0. So we're gonna consider, if this is the ground, we will assume that this is the PE level, and in particular at this level the potential energy would be 0, which means ui, which corresponds to the initial vertical position, would be 0, and by that the final potential energy given at the final vertical position is given by mgh. Similar argumentations can be done if the object is below a chosen PE level, and it happens that the gravitational potential energy UG in this case below the PE level is said to be negative, and this is independent and it has nothing to do with the origin of the y-axis. Now we're ready to summarize the results. If an object of mass m is near the surface of a planet, or in other words placed in uniform gravitational field G, then our system mass planet possesses a gravitational potential energy given by UG. First of all, as we have done, a PE level must be chosen in order to define the zero potential energy, and this is usually done by the lowest horizontal level given in our system. If the object lies above this PE level, for example like that, we have an object which is at a distance h above the PE level, then the system possesses positive gravitational potential energy given by mgh, where h is the vertical distance between the center of mass of the object and the PE level. If the center of mass of the object lies on the chosen PE level, that would give us 0 gravitational potential energy. If the object lies below the chosen PE level, then the system possesses negative gravitational potential energy given by minus mgh, where h is the vertical distance again between the center of mass of the object and the PE level. Now what about gravitational potential energy between two massive bodies? We know that mgh is or the force of gravity given by mg is a simplified version of Newton's universal law. Now let's consider the case in which two objects of masses m and m are separated by distance r. We're talking about the center of mass separation distance. The two objects can be understood as a planet of mass m and a moon of mass small m. Then the system mm possesses a gravitational potential energy Ug for the similar argumentations that we have done. The aim of this section is to determine the expression of Ug between the two masses. Previously we have determined the expression of Ug, and it's given by mgh up to a plus or a minus sign if we're above or below, but remember that this expression only works if we're near the surface of the planet. Now the pull of gravity between the two bodies is given by minus g mm over r square. The negative sign indicates that the pull of gravity points radially inward. So here the minus sign is very crucial because we're interested in integrals and calculus, and we need to indicate the specific direction. The minus sign, it means that it will be pointing opposite to the radial direction. So what does the radial direction means? Now here in such type of problems we need to choose the origin to be either the big body or the small body. We usually take it to be the more massive body. Then that would be the radial direction, and the positive radial direction by default would be away from O. But we know that the pull of gravity will be pointing toward the massive body. For this reason we have associated with it a minus sign. The gravitational potential energy Ug can be determined using this relation again, where Ri is the initial position and Rf is the final position. Replacing in the above integral we get, now we can split delta U to be U final minus U initial in correspondence with the initial and the final radial position. And now the pull of gravity has been replaced by this integral, by this function. Now minus with minus they would cancel, and we're left with the following. Now we need to integrate the following function. Now gmm is a constant, it can be dragged out. We're integrating 1 over r square, which can be utilized as a power function r to the power minus 2 dr. We don't forget this. Now we increase the power and we divide by the final power. That would be r to the power of minus 1 divided by minus 1, which is basically minus 1 over r. And we multiply by the factor which is gmm between final position and initial position. Now let me do that carefully for you. You can factor out minus this to be out, and our variable is 1 over r computed between initial position and final position. We're talking about radial position. That would be minus gmm as a factor out, 1 over r final minus 1 over r initial. Now multiplying by the minus sign inside, that would be gmm 1 over ri minus 1 over rf, which is basically what has been represented here, because minus with minus would become plus. So 1 over ri minus 1 over rf. Now here we need to choose our reference potential energy as we've done near the surface of a planet. Now you can think about the following. If the separation distance between the two bodies is large enough so they don't communicate with each other, then the pull of gravity between them is 0, so no potential energy is stored. So we can say for a very large separation distance, as Ri tends to infinity, the system loses gravitational potential energy G and it vanishes, which means Ui is 0. Now here, how do we know whether the infinite position corresponds for the final or the initial, it depends on you. So for example, in my case, I will choose the initial position to be infinity. So in this case, that would be infinity, which means this is 0 overall, because any number over infinity, that would be 0. And because I have chosen the initial position to be the infinity, which means ui would be 0. And we're left with the following result. Now what about choosing the final position to be the infinity? So let me explain here. So let me refer to this equation. UF minus UI is minus GMM over final position plus GMM over initial position. I will go with the final position to be infinity, then that would be 0, then that would be 0, which means that minus UI is GMM divided by RI. Again, the potential energy in this case is given by minus GMM over RI. Then whether we choose our reference level with whether initial or final won't make any difference, because we're gonna rename everything again whenever we finish these results. Which means that a system consisting of two bodies of masses m and m are separated by distance r admits a gravitational potential energy given by minus GMM over r, where g is the gravitational constant and is given by the following number. Now we're done with these. Exercise 1. A small mass is released from rest at a very great distance from a larger stationary mass. Which of the following graphs best represent the gravitational potential energy of the system of the two masses as function of time? You need to pay attention, because functions, they can be graphed according to different parameters. So we have determined u to be given by minus g mm divided by r. So if we're plotting u as function of r, we would get a certain graph. If we're plotting u as function of time, we'll get another graph, and this depends on our initial and final conditions as well. So here let me do a figure. So this is the big mass and this is the small mass. Initially, what's happening at t is equal to 0, they are separated by a very great distance, which means initially the potential energy is given by 0, because for a very great distance r would tend to infinity and the potential energy would be 0. So if we were starting from 0 potential energy, and we can directly eliminate the choice C. Now u is negative, which means that we are limited either to C or to B or to D. We're gonna directly eliminate A. We know that, so sorry, we can also eliminate C because C is positive. But we know that it is not linear, it is 1 over r, so it will have the following plot. So we can eliminate this, then D will be the correct answer. But let's continue the argumentations even more. As we leave this system from a very great distance, if m, the mass m, is not given any initial speed to perform orbital motion, then we expect that m will fall into the larger planet, which means as it goes down, as r increases, we expect that the value of u, because it's negative, it will increase. Alright, the values of u as values, they are decreasing, but because we have a negative sign, the values of u are increasing. So which best represents the graph D. Exercise 2. To stretch a certain nonlinear spring by an amount x requires a force F given by 40x minus 6x squared. Now, if you look at the following force, we need to pay attention whether this force is the magnitude or the restoring form. However, because the choices are given in all they are positive, so no need to worry about the minus sign. However, now we're gonna refer to whether it's stretched or compressed to do the linkage, where F is in newtons and X is in meters. What is the change in the potential energy when the spring is stretched? So stretch means away, which makes the work to be positive. Which makes the work to be negative, which means that the change in the potential energy is positive according to the previous class, because delta U is given by minus the work done by the force. For this reason, all of these changes are given by positive changes. And also, moreover, you know that whenever you stretch or compress the spring, this would store an elastic potential energy in the spring, which makes the change in the potential energy to be positive. Now we're asked about the change in the potential energy. This is straightforward and can be calculated using the following relation. Delta U is minus the work done by the force, which is minus the work done by F dot dx from an initial position given the equilibrium to a final position given by 2 meters. Now we can replace the force F to be given by 40x minus 6x squared. Now we can directly take this minus sign to be inside the integral. That would be from 0 to 2 of 6x squared minus 40x dx. That would be 6x cubed divided by 3 minus 40x squared divided by 2 from 0 to 2. We can even simplify it more. That would be 2x cubed minus 20x squared computed between 0 and 2. Now we will compute this expression twice, once at 2 and once at 0, and we will consider the difference starting with 2. Now that would be 2 to the power of 3 minus 20, 2 to the power of 2 on one hand, minus 2 multiplied by 0 to the power of 3 minus 20 multiplied by 0 to the power of 2. Now all of that would be 0, and we're left with this. Let me calculate it here. That would be 2 multiplied by 8 minus 20 multiplied by 4. That would be 16 minus 80, which is minus 64, because all of these are energy. That would be joules. Now why our answer is negative? Because the force that we have considered here is the magnitude and it's not the restoring force. So in order to avoid this minus sign, we should multiply this expression by minus, and in this case the correct answer is D. Now the graph above shows a conservative force F as function of position x. Now let me do the following interpretation. The work done is negative because the area is negative, so the work done is negative, which means that the change in the potential energy is positive. What happens to the potential energy of the system as the object moves from 0 to 0.1 meters? It increases only. Why it increases? Because the variation is positive, which means U final minus U initial is positive, which means U final is greater than U initial. Now exercise 4 as an exit ticket. The potential energy U as function of the position x of an object is given by Ux is minus 400x, where U is in joules and x is in meters. The object is released from rest at position x is 30 meters and it's free to move along the x-axis. So let me draw the following figure. This is the x-axis, this is the origin, this is the position. Now 30 meters would be located somewhere here. Initially the object coincides with this position. When the object has moved at a distance of 10 meters from its initial position. Now here we should be very careful. They're telling us the object has moved a distance of 10 meters. So it can move either 10 meters to the right or 10 meters to the left. How do we determine the direction of motion? This is related to the direction of the force. Remember that here we're talking about conservative forces, and conservative forces basically point toward the least potential energy. Now the potential energy is given as function of x. Now you can consider two limits in which x is very small, like minus 400 divided by 0.01. That would give us, for example, minus infinity. And if you consider x to be very large, like infinity, minus 400 divided by infinity, that would be almost 0. So if we're trying to compare the potential energy at the origin and at the potential energy at the infinity, you can notice that the potential energy at the origin is less than the potential energy at infinity, which means the force will be pointing toward the least potential energy, which is toward the left. Then for this reason, the object will move 10 meters toward the left, and its position would be given by 20 meters, which is somewhere here. They're asking us to calculate the magnitude of the force associated with this potential energy at which position when the object has moved 10 meters. 10 meters to the left. 10 meters to the left makes the new position to be 20 meters. Then we know that the force can be determined from the potential energy via derivative. Then Fx would be given by minus du divided by dx. Now this can be understood as an operator, taking the function minus 400 divided by x. Minus and minus would cancel. We can take 400 out. That would be d by dx of 1 over x. This can be utilized as a power function x to the power minus 1. If we're trying to derive it, that would be minus 1. We drop down and we decrease the power by 1, and that would be minus 1 over x squared. Then that would be minus 400 divided by x squared. Basically, x is a variable which represents the position. After we have moved 10 meters to the left, the new position would be 20 meters. Then that would be minus 400 divided by 20 to the power of 2, and that would give us minus 1 newtons, because we're interested in the magnitude of the force, which makes D to be the correct answer. Then that's it for me in this video, guys. See you soon in a new one.